This unit is on human body models. Humans interact through their bodies, as illustrated here on the slide, which is a slide I took from Michael Black, who is a Max Planck director here in Tübingen and who has dedicated a lot of his research to understanding and modeling human bodies. And modeling and understanding human bodies is important if we want to understand what humans do, but also in order to interact with humans. So here I see some of the interactions that humans do: hugging, collaborating, dancing, interacting with their environment, etc. And what we're going to discuss today is the so-called simple body model, SMPL. And the simple model is maybe one of the most popular models these days in the research community and a foundation for many follow-up works. And it's a generative human body model. And the goal of this is to create a model of, minimally clothed human bodies. Clothed human bodies is harder, so this model focus on the human body itself. So it focus on people in minimal clothing, as you can see here. And that the goals for this model are as follows. The reconstructions from this model should look like real people, right? Of course, we want to build a model that's precise. It should also allow for deformations that look like deformations of real people. It should have a small number of parameters so that it's easy to represent and to store and to manipulate. And it should be easy to fit to data, because we often want to fit this model to scans or to images in order to understand humans. And it should also be easy to animate, because often we are also interested in taking a character, an avatar that we have generated, and animating that character, for example, in the context of generating movies or video games, etc. Yes, so here, this is the model that we'd like to obtain. M, the output, is represented in terms of 3D mesh. And that mesh depends on the pose and the shape and the dynamics and the texture and some parameters, right? Some general parameters of that model. Here's an illustration. On the left, you can see a real image, and on the right, you can see the reconstruction of that simple body model in terms of both the geometry and the appearance. And you can see that this reconstruction is matching the input image quite well. And in this unit, we are going to discuss how this is done. Modeling of human bodies, human shape and pose has a long history in computer vision, starting from, well, the 70s and 80s. And the question is, of course, what is a good representation? So the representation that the simple body model focuses on is a representation of not the interior of the human body, but the human body as it can be observed. Basically, the minimally clothed human body, but to represent that minimally clothed human body as accurately as possible in terms of geometry and appearance. And a big inspiration for the simple body model was the seminal work by Blans and Vetter in SIGGRAPH 1999 on human face models. That is a precursor, if you will, of the simple body model, but for a specific part of the human body, for the face. And there's a little old video from this technique, which is still amazing to watch these days in terms of the accuracy that this model has achieved. So I want to play this video for a little while so they can get an idea of what this method is doing and what it's capable of.
The Morphable Face model is derived from a data set of 200 colored 3D scans of faces. Individual faces are combined into a single morphable model by computing dense point-to-point correspondences to a reference face. A modified optic flow algorithm establishes 3D correspondence automatically. The morphable model combines 3D shape and texture information of all example faces into one vector space of faces. We can form arbitrary linear combinations of the examples and generate continuous transitions. Starting from the average face, individual original faces are caricatured by increasing their distance from the average. Forming the average for male and female faces separately, the difference can be added to or subtracted from an individual face to change the perceived gender. Other facial attributes, such as the fullness of a face, can be manipulated in a similar way. From a labeled set of faces, the characteristic changes are extracted automatically. In our model, they're controlled by a single parameter. Differences in facial expressions captured from another face can be mapped to any individual. We now reconstruct 3D shape and texture in order to animate a face, given only a single photograph of a person. First, we manually align the average face to the target image, roughly estimating position, size, orientation, and illumination. Then, a fully automated algorithm finds the best reconstruction of the face within the morphable model. 3D shape and texture are optimized along with parameters such as size, orientation, and color contrast. The output is a high-resolution 3D mesh of the face. It is an estimate of 3D shape and surface colors based on a single image. Additional texture extraction improves details in texture. The reconstruction can now be rendered into the image, and a whole range of facial variations can be applied. Here we simulate weight gain and weight loss. Facial expression can be post-processed in images, forcing a face to frown or to smile. From this image, we also estimated 3D shape and texture and combined the photograph with 3D computer graphics. Cast shadows of novel objects are rendered correctly into the scene. Illumination conditions can be changed, and pose can be varied to some extent. From a single black and white image, we obtain a full estimate of 3D shape. The result of the matching procedure includes an estimate of surface color, since the morphable model contains color information. Finally, we show the application of our model to a painting.
This was 1999, more than 20 years ago. Quite impressive. Okay, so let's dive into SIMPLE. SIMPLE is an acronym for a skinned multi-person linear model. And the idea is, as in the previous video, as we've seen, to take scans from a big human body scanner, take many of these scans, and to create a generative 3D model out of those. And to create this model in a way such that it is factored, that we have different controls for pose and shape, dynamics and breathing, and all the other factors that we might be interested in. So here's an example to illustrate this. You can see a character, you can see the geometry. So I want you to focus on the geometry here on the top. You can see on the left that the pose is fixed, but only the shape is varied. In the center, the pose is fixed, the pose is varied and the shape is fixed. And on the right, both the shape and the pose vary. So you can see how these factors are disentangled in the model and can be independently controlled and give rise to such generations here. So let's now look at the technical details of this model. SIMPLE uses a 3D mesh as an output representation. And as we know, a mesh is represented through vertices and faces. The base mesh is designed by an artist to match the majority of human bodies well. And the mesh has 7,000 vertices, which yields a representation with 21,000 numbers. Each vertex is a 3-dimensional vector. And so we have 21,000 numbers to represent the human body. This is the space that we want to operate in, but it's of course a very high-dimensional space. It's not as high-dimensional as typical images, but still very high-dimensional. And via that, it's clear that most settings of these numbers do not really correspond to people or any shapes, but just random noise, random garbage. So we want to find now a sensible setting of these numbers that corresponds to shapes in the data set that we've used to train our model. That's the goal. In order to do so, as a first step, we need to do something that's called mesh registration. The raw scans are just unordered and incomplete 3D points. They can be meshed, but you will see they have many artifacts and holes as illustrated here. And to get correspondences, a template mesh, this template mesh designed by the artist, must be aligned with each scan. And this is a hard problem. It's actually a chicken and egg problem because you require the body model, the trained body model with the parameters in the first place to deform it towards the input, towards the observations. But you also require the observations to train the human body model, right? The registered observations. And the solution here that is taken by the simple body model is to solve model and registration, to solve model estimation and registration jointly. Now, let's for a moment assume that we have already solved the registration problem and that this allows us to convert all the scans that we have obtained from the scanner into a canonical pose. And that pose is this A pose, called A pose here because the arms are in this A position. Then we can basically we can transform each of the scans into this A pose as illustrated here. So these are the raw scans transformed into the A pose. And then we can fit this body model to these scans in A pose. And what we have then is basically we have this body model. We have this 3D mesh, which is a collection of these 21,000 numbers of these 7,000 vertices. So if we vectorize the vertices, the mesh vertices, we call them T. We subtract the mean mesh, take the average of these vertices. And this is the colored model that's illustrated here, and we're going to subtract that. And then we can apply a principal component analysis to yield a linear model of this, right? So we can stack these into the columns of a matrix T. Then we can decompose that matrix such that these observations are linear combinations of some basis shapes, and these are called the blend shapes, that are combined linearly with these weights beta here. And these weights beta now are very low dimensional compared to this original 21,000 dimensional representation. These weights may just be 10 dimensional or up to 300 dimensional to express most of the variance of the observations. So we can now, using PCA, because we have assumed that the body is in a canonical pose, we can reduce this problem and obtain a 10-dimensional latent space that expresses most of the variance in the data. What does that look like? This is an example of variation of individual principal component, principal vectors. You can see that in the beginning, when we vary the first principal component, then the size of the character changes. If we vary the second principal component, we see that the size of the weight of the vector character changes. And then if we go on to additional principal components, we see that smaller details start to change. And this is what we expect, because the first principal component explains most of the variance in the data, as we know. However, of course, we do not have all of these, as initially explained, all of these observations registered into the same coordinate. And so we have to solve this chicken and egg problem, where we are solving for both the registration and the model parameters jointly. And that's what simple does. So simple solves also kind of a PCA problem, but at a larger scale, by also deforming the template mesh. And how it deforms the template mesh is it uses a extension of so-called linear blend skinning. So we first need to understand what linear blend skinning is. In linear blend skinning, the goal is for each vertex on the template mesh to find the transformation to the mesh in target pose, as illustrated here on the right. So here we have a template. This is in T pose. We want to find for each of these vertices the transformation that transforms, or for each point on that surface, we want to find the transformation that transforms that to the corresponding point on the surface in target pose. And we're going to do that through this linear equation here. This is just a sum over some weights. These are called the blend skinning weights, times a rigid bone transformation matrix. That's just a rigid transformation matrix with 6 degrees of freedom that depends on the pose parameters and the joint locations. And we're going to multiply this with the input point t. So we take this ti, and by this linear combination with this weighted combination of these g's, we're transforming that point here. So what are these g's, this rigid bone transformation? This is illustrated here. So in different colors here, you see different bones. Let's look at, for example, this green bone here, which is the right upper leg. And this green bone here, which is encircled by this ellipse, is transformed using a rigid body transformation to that green bone here, which is the same bone, right? And we call that This is the cave bone. We call the transformation, that rigid transformation, GK. So any point that lies on the surface of that bone should be transformed according to that bone transformation GK. So we simply transform that point by multiplying TI with GK. And the weights, which are this colorful representation on the surface of the human body, indicate how much each of the bone influences that transformation. So if you take a point that's in the center of that body part, K, then all the other weights will be 0 except for the weight of that particular bone, of that particular body part. But what happens if we take a point that's in between two body parts? Let's say this point, which is in between the red and the blue body part. Well, in this case, the weight of both the red and the blue body part will be high. Both will be 0.5, let's say. But all the other weights of all the other 25 or so bones or body parts will be 0. So we have a linear interpolation of the transformations, these rigid body transformations of two adjacent body parts or bones. And this is necessary because we have a non-rigid transformation. So we need to interpolate. Whenever we have a joint, we need to interpolate between the rigid transformations that are induced by the two adjacent bones. Right? And these rigid bone transformations, of course, depend on the pose, theta, and potentially also on the joint locations, J, because depend on the size of the character. But in particular, we depend on theta because if you think about this as a kinematic tree, if I change this joint here, the elbow, then of course the corresponding child part or child bone transformation is also affected by this change of the joint in the kinematic tree. So this is how linear blend skinning works. It's basically a linear blending of rigid bone transformations where points that are in between two adjacent bones receive receive transformations from the two adjacent bones such that there's a smooth transitioning happening. Now, how are these skinning weights obtained? Well, the answer is simple. In practice, they are typically obtained by an artist, and the artist manually, in a careful process, designs these skinning weights such that they are leading to realistic post-human body shapes. But that is a difficult task, actually. And a particular configuration of skinning weights doesn't lead to very nice deformations. It cannot be guaranteed to lead to nice deformations for arbitrary body poses, as you can see here. So if you look at the elbow, for example, the deformation that's happening at the elbow is appearing very unrealistic. And the cause for this is really that this linear blend skinning is too simple. It's not enough to just linear blend the transformation of these two bones, because you will get effects like this. It's also illustrated in this video here. We have linear blend skinning on the left. You can see these effects. And you have the simple body model, which we're going to talk about in a second, on the right, which is a generalization of linear blend skinning, which doesn't suffer as much from these effects. You can see a much more natural shape appearing. So what does simple do differently from linear blend skinning? This is LBS, linear blend skinning versus simple, or simple versus linear blend skinning. On the left, we have the same illustration as before. And here, this is the formula from the previous slide, which is the formula for linear blend skinning. And on the bottom, you can see the formula for simple. And in red are highlighted the 3 key differences. The first key difference is that because simple is a model for multiple bodies, while LBS was typically applied to a single character, simple now has to handle many characters. Of course, the joint locations must depend on the body shape. There's tall people, there's small people, and of course the bone length and therefore also the distance between joints must, and the location of the joints in the canonical, say, T-pose template must depend on the body shape. That's why J now depends on the body shape, and it's regressed effectively from the body shape. And then two additional modifications are so-called correctives. In addition to simply take that point Ti on the surface in the canonical rest, what's called the rest pose, and transform that point to yield Ti prime, what is added to that point Ti already in the canonical space are two correctives, a shape corrective S and a pose corrective P. The shape corrective allows the model in the rest pose to accommodate different shapes, to accommodate heavy people and to accommodate thin people, for example. And in order to model the shape variation, of course, we have to change the location of the surface point. And we have to model that. And that depends on the shape parameters, which are called beta. And the last difference here is this pose corrective. As we have seen previously, a major limitation of LBS is that it is too simple and that there's many artifacts. If we just take this linear combination of at a joint of two adjacent body parts or bones, if we take the linear combination of this rigid body transformation G, of these two, this is too simple and it leads to these artifacts that we have seen. So what simple does instead is it adds these pose correctives, which are also changing the shape of the human body in the rest pose, but it's changing it not based on the shape parameters beta as the shape correctives do, but it's changing it based on the pose parameters theta. So you get also a pose dependent corrective to the shape in canonical or in rest pose. And these two models are linear. This is a little simplification here of what the model actually does. It actually uses not the, let's say, the joint angles directly, but it uses a bit more clever representation of the joint angles, but still it's a linear model in this representation. And then this model is trained on a big data set and optimized for the parameters of that model, which are the basis shapes S and the basis pose correctives P. So basis shape correctives and basis pose correctives. In order to yield the final model, and of course also in terms of the other parameters like what LBS is optimizing for the pose, and the skinning weights are given. Yeah. So here's an overview of the data set. This is just a little glimpse on all the scans that have been used for training that model. It's enormous. It's a large data set of several thousands of shapes. And here you can see an illustration of what the model has learned, in this case, in the context of blend shapes. So you see what happens if the animated, this is a generated geometry from the model, the animated model, what a change in the pose of that model induces on the shape in canonical pose. And you can see that due to the pose dependency, because we want this final generation result to look good, don't have these artifacts that are induced by LBS, the shape in the canonical in the rest pose is modified accordingly to compensate for these effects. And this is what these pose correctives, these PostBlend shapes do. So it's basically all the big PCA model just factorized into these different components. Some depend on shapes, some depend on pose. And here's the result of what this model can do. So you can see different identities, different people performing the same action through this simple human body model. It's a very precise representation of the human body shape, and it can be fitted to many different people. The model can be used, for example, to retarget characters. Here's an example where there's a motion, the original body shape on the left, and there's a retarget motion for a different shape here on the right. You can see that the person is moving accordingly, but with a very different shape as the input character. The model has also been extended in various ways, actually. So this is just one extension. It's called Dimple, Dynamic Simple. In particular, for taller people, for people with more weight, you have soft tissue deformations that depend also on time. This can be modeled by taking time into account, as you can see here. Now, this model cannot just be used to generate artificial characters, but it can also be used to more precisely estimate the shape of humans by just looking, for example, on a single RGB image as shown here. And there's a little video for this. You can see the pose and the shape that has been extracted for the people that are visible in these images here on the left. Of course, if you estimate human body pose and shape from a single image, there's a lot of ambiguities to resolve. The more views you have, the better, or if you have depth data, that's also helpful. But in this case, it's estimated just from a single image, and you can see that the model quite successfully is able to reconstruct pose and shape due to its prior knowledge, because it has been trained on this big data set of 3D human scans. Now, this is of course not the end of all of human body modeling. There's a big research community in the computer vision community that's just concerned with this problem. And some of the current research directions, as illustrated here, include modeling of clothing, which is much harder than the naked human body or minimally clothed human body. Modeling of garments, realistic modeling. There's a lot of stochasticity involved. Also modeling of appearance. Many of these models that I've shown to you didn't include appearance, but of course appearance is important if you want to realistically render these. Modeling of dynamics, few shot learning just from RGB images, and building avatars from very little data, like maybe just from your webcam observing yourself, and inserting them into maybe a video game or a virtual reality application. Interaction, for example, interaction with other humans, with other avatars, or with 3D environments.